Welcome everyone. I am Muhammed Unais from Indian Institute of Technology, Bombay, and I will present our ICP 2021 paper, SymFlex, Elastic, Persistent and Symbiotic SSD Caching in Virtualization Environment. This is a joint work of myself and Professor Purushottam Kulkarni. The main requirement of a storage media are the low latency and persistence. The figure shows the conventional storage hierarchy in the computing world. While the computing world is waiting for the arrival of the new environment-based technologies to meet the storage requirements, the flash devices-based technologies have fulfilled the same requirements for the last couple of decades. They are widely used as a cache layer between slow and persistent magnetic disk and fast and volatile main memory devices. The domain of this work is use of the SSD devices for disk I/O caching in virtualization-based hosting services. There are different ways in which SSDs can be used for caching, and it can be configured at various layers in the I/O path. The more popular configuration is the host-side caching. In this configuration, SSDs are used to cache the data stored either in the locally attached hard disk or a network-mounted disk, and the caches are shared across multiple VMs. In this case, the hypervisor has a complete control on the cache device, and it can easily perform different policy and performance control decisions over this shared caching. The other method is client-side caching, where the SSDs are exported to the virtual machine and the caching is done within the VM. In this case, the cache layer can perform application-specific or the guest-specific decisions and policies on the caching, as it is aware of the semantics of the data stored in these cache devices. In addition, different VMs can use this SSD device to cache different kind of objects. In one VM, it can be a block-based cache. In another VM, it can be a file system metadata cache, or etc. In IaaS-based hosting setup, the keys for win are overcommitment and dynamic provision of resources. There are different virtualization techniques to allocate more resources to the VM than it is available in the physical machine. Similarly, CPUs, memories, and other resources can be dynamically provisioned to the VMs on the demand. For example, the memory allocation of a VM can be changed using demand paging and ballooning-like techniques. In this way, like any other resources in the system, the SSD-based caches need to be dynamically resized to account for the load in the VM, the performance metric, and other usage policies. This is a small experiment to motivate the need for application-aware cache elasticity. The adaptation policies to dynamically change the cache allocation can be of two types: black box and gray box approaches. With the black box policies, the hypervisor is unaware of the cache semantics and its utility for the VM. In this case, the hypervisor employs VM agnostic policies to manage the hypervisor-based caching. Gray box policies depends on the information and actions from the software entities within the VM to execute the provisioning policies. The experiment shows the hit ratio of a cache in VM agnostic black box and VM managed gray box policies. The FIO tool is used to generate the workload in both cases, and it assesses a 500 GB hard disk. In the first window, 80% of the accesses are from the first 34 GB of the device and the 20% from the remaining portion of the device. At the end of each window, the working set size is shifted to the next 34 GB of the device. In addition, the cache size is reduced by 4 GB at the end of each window. The black box approach employs an LRU-based caching policy, while the gray box approach is aware of the shift in the 34 GB working set size. So, the gray box approach tries not to evict the cache blocks of the next working set during the resize at the end of a window. Since the gray box is aware of the cache data semantics, it provides increased efficiency during the cache resize. As we explained in the last two slides, the main requirements of high utilization of a caching in IaaS setup are a mechanism for dynamic resizing and usage of semantics of the software stack using the cache. Now the question is, who is going to resize the SSD? If the hypervisor does the resizing, it operates in a VM transparent manner, and it cannot completely leverage the cache usage semantics and the load behavior within the VM. For example, the hypervisor doesn't have any idea on the type of the objects cached and their relative importance. If the guest manages the cache, it can use the cache usage semantics for better eviction decisions. But the existing SSD virtualization techniques are statically sized and lack the elasticity feature during the runtime. So for the optimal performance, let the hypervisor to manage the SSD resource across the VMs and the operating system to manage the evictions based on the cache usage semantics. To support this symbiotic game plan, the main challenges are the lack of an elastic SSD virtualized device and a framework for symbiotic management of the cache by the hypervisor and the software entities within the virtual machine. So we propose SymFlex, an SSD-based elastic and symbiotic I/O caching framework for virtualization environments. This figure shows the architecture of the SymFlex. The main three components are virtualized elastic VSSD device, the hypervisor-based SymFlex manager, and the VM-specific elastic SSD manager. The first component is involved with setting up their special device for the virtualization and the necessary virtualization support for control and data communication channels. The VSSD virtualization include a device specification, a front-end driver within the VM, and a back-end driver at the host. These two drivers coordinate each other to configure the VSSD device and for the I/O and resize operations on the device. The next component is SymFlex Manager and is responsible for managing the SSD resource across several virtual machines. A resize engine, a policing engine, and a block manager are the three sub-components of the manager. VM-specific Elastic SSD Manager is responsible for managing the VSSD-based caching store. The manager performs different caching and eviction policies. So whenever we start a VM, the VM first registered with the SymFlex Manager. The registration request specifies the VM ID, the maximum size of the VSSD device, and its current allocation size. Now let's look at how the I/O operations are performed in the SymFlex. The SymFlex considers the VSSD device as a series of logical blocks and the physical SSD device as a series of physical blocks. We fixed the size of both logical and physical blocks to 1 MB, and the resource allocation happens at the granularity of this 1 MB. That is, each block contains 2048 sectors. Consider an application issues a read request with file descriptor, the offset, and the size to be read. The request passes through different intermediate layers and the front-end driver receives the corresponding BIO request. The BIO request specifies the VSSD device, the sector number, and the size. A read request can span over multiple logical blocks. If a physical block is not allocated for any one of the logical block, the request is considered as an invalid request. For a valid request, the front-end driver forwards the request into the back-end driver. The back-end driver divides the request into sub-requests if the request crosses the physical block boundary and issues separate requests to the physical media for each physical block in the request. Suppose an application is trying to read the sector 5000. It is the fourth sector in the second logical block. Since the second logical block has a valid mapping, the front-end driver forwards the request into the backend. In the backend, the corresponding physical block number is 10 and it issues a request to read the fourth sector in the 10th physical block from the physical SSD device. Let's look at the dynamic resize path with the SymFlex. The SymFlex Manager initiates all resize requests by sending a resize request to the backend driver. A resize request contains number of blocks to be evicted or inflated and the type of the resize operation. Suppose the SymFlex Manager wants to deallocate 2 blocks from a VM, then it sends a degrees request for 2 blocks to the backend driver. The backend driver forwards the same request to the frontend driver and the frontend driver forwards the request to the VM specific Elastic SSD Manager. It can be an application or an OS subsystem. The cache management unit executes its own policy to decide the blocks to be freed and forwards the list of logical blocks to the frontend driver. So in this case, the list contains logical blocks 2 and 3. The front-end driver resets the corresponding bits in the bitmap and forward the list to the backend driver. The backend driver invalidates the logical to physical block mapping for the corresponding logical box and forwards a list of freed physical blocks to the SymFlex manager. The manager moves those blocks from the VM specific list to the free pool. In this case, the physical block numbers corresponding to the logical blocks 2 and 3 are 10 and 13. It invalidates a bitmap at the location of 2 and 3 and forwards the physical block numbers 10 and 13 to the manager. Increase in the VSSD size happens in the reverse order. You can find its more details on the paper. To demonstrate the efficacy of SymFlex, we modified two existing applications to operate with an elastic SSD device. The first one is a DM cache and the second one is a fat cache. DM cache is a device mapper based cache to store disk IO blocks. With SymFlex, we employ the VSSD device as a cache device and we kept the elastic SSD manager as part of the DM cache in the block IO layer. Further, SymFlex extended the DM cache also to provide the support for differentiated provisioning of VSSD cache across multiple applications. To provide this functionality, we leverage the C groups in subsystems in the Linux to specify the weights for proportionate sharing of the VSSD cache across multiple applications. The second use case is a fat cache. It is an in-memory key value store which uses the SSD to extend its capacity. We modified the fat cache to support the elastic SSD device. In this case, the cache manager is residing in the application layer and the front-end driver communicates with this manager to perform the resize operations. Moving on to the evaluation section. Some important questions like, does the VSSD affect the IO virtualization? What is the payoff with symbiotic management of the SSD caches? And how flexible are the different caching and resize policies? Some of these questions will be addressed as part of this presentation, and please refer to the paper for the full set of the experiments that we have done. For the experiments, we use KVM plus KEMU platform and the FIO tool is used to generate the IO traffic. The use cases fat cache and DM cache are used to demonstrate the efficacy of the symbiotic management of the VSSD device. First, we benchmark the elastic VSSD device. This experiment compares the raw performance of the VSSD device with the existing two virtualization techniques. The wood IO raw means SSD is directly exposed to the VM as a raw device. Wood IO ext2 plus QQ2 means a QQ2 disk image stored in a ext2 partition is exposed to the virtual machine. We configured a VM with a 2 GB RAM, 2 vCPUs and a VSSD of capacity 20 GB, and we used the FIO benchmarking tool to issue the file IO request to the VSSD. The FIO reads 20 GB worth of data with multiple threads from the VSSD device. The first graph shows the throughput achieved for different FIO read granularity and the second graph shows the performance for different read-write ratios. From these two graphs, it is clear that the VSSD implementation overhead is minimal and its performance is comparable to the existing virtualization methods. The next experiment characterizes the resize latency of a VSSD device for DM cache and fat cache. The setup was a virtual machine running one of the two use cases at a time and a series of VSSD requests were issued. We performed experiments on both DM cache and fat cache setups by varying the granularity of the resize operations, and we measured the total time taken and the time spent in both front-end and back-end drivers. The figure shows the diffraction latency of the two setups. The latency of the fat cache is around 2 to 3 times more than that of the DM cache, and this is because in case of a fat cache, each resize request has to cross the user space or the user kernel space boundary. This experiment demonstrates efficacy of SymFlex for an SLA-based provisioning of SSD resources across virtual machines. This figure shows a proportionate throughput-based cache provisioning across four virtual machines. In the experiment, the SymFlex is configured to allocate maximum of 100 GB of SSD space across 4 virtual machines. The experiment consists of 4 windows and the VMs are configured to operate with varying IO throughput ratios and the cache requirements in these 4 windows. In the first 3 windows, all the VMs are having similar working set and the required throughput ratios are varied. In the first window, when all the caches are warmed up, the policy engine starts enforcing the configured ratios of I/O throughput by resizing the VSSD associated with each virtual machine, and the measured throughputs are in the same ratio. In the window 2, the required throughput ratio is changed to 4:2:3:3, and the manager allocates more blocks to the VM to enforce the same ratio. Similarly, in window 3. In the last window, the working set size of the VM3 is reduced and that of the VM2 is increased. This resulted in allocating less number of blocks to the VM3 and more blocks for the VM2 to maintain the same ratio on throughput values. This experiment evaluates the dynamic cache provisioning across nested applications. There are two virtual machines with each running two instances of a file system workload in separate C groups. Initially, a total of 100 GB VSSD space is allocated across the two VMs in the ratio of 1:2. The applications 1 and 2 in the VM1 and the application 3 and 4 in the VM2 shares their cache allocation in the same ratio, that is 1:1, and I/O throughput of these applications behavior in the same ratio. In the second window, we changed the cache allocation across the applications in VM2 to 1:2 ratio, and their corresponding throughput is changed in the same ratio. In window 3, the cache size across the VMs is reduced by 20 GB and the I/O throughput of the application behaved in the same ratio, that is, with the overall ratios across the VMs still adhering to 1:2 ratios. So let me summarize it. So we designed and engineered a new mechanism to virtualize the SSD devices with the elasticity feature. Also, we demonstrated the efficacy of these frameworks to symbiotically manage the elastic SSD resource across several virtual machines. And our immediate extension for this SymFlex work is to provide the support for the SSDs in the network and then to enable the line migration feature with the elastically virtualized SSDs. Okay, thanks for watching it and feel free to contact us for any questions.